Hi, hello everybody, welcome back to another video. It's me, David aka W, and today we're asked to compute the integral of f along this curve C, where C is a curve from P to Q as shown in this figure. And while this may look like it's going to give you some trouble, once you start breaking this apart, this is actually a really easy integral to solve. So let's go ahead and remind ourselves the fundamental theorem of line integrals. The fundamental theorem of line integrals tells us that given that our vector field is conservative and that C is a piecewise smooth curve in an open region R, we can solve the integral, this integral, just by finding its potential function and subtracting the starting points from the endpoints. What this tells us is that for us to apply this theorem, we need to hit the conditions that f is conservative and that C is a piecewise smooth curve in an open region R. We can see from this figure right here that our curve C is a piecewise smooth curve. What this means is that our curve is written as a union of a finite number of smooth curves. Here where we have three curves, P to R, R to S, and S to Q. And this just makes a piecewise smooth curve, P to Q. So that's one condition satisfied. Additionally, we need to check that f is conservative. And to make sure that our vector field f is conservative, we just have to make sure that our curl is equal to 0. Remind ourselves that our curl is just the cross product between the gradients and our vector field. And you don't have to worry about this. I just have it here for reference. But this is if it would be the case that our vector field was in 3D. But since our vector field is in 2D, and the reason I know this is because there's only two variables here, and also because it's made of the I vector and the j vector, and those are only two. So we're going to go ahead and use the curl of f, given that it's a 2D vector, and try and find that when it would equal 0. So here's just the math that I did. But this is our curl of f. And to make sure that it equals 0, let's just make curl of f equal to 0, and we would just be moving the partial derivative of p with respect to y to the other side. That way we would get that for curl of f is equal to 0, the partial derivative of p with respect to y has to equal the partial derivative of q with respect to x. And once we satisfy these two conditions, we can go ahead and determine our potential function. What this tells us is that our vector field f is equal to the gradient of our potential function f. So our vector field can be rewritten as this. Not really rewritten, it's the exact same thing as this. And to determine a potential function of f, we just have to take the integrals of these two different variables, and we'll use that to figure out what a potential function f is. And let's go ahead and check. Let's go ahead and first check that our vector field is conservative, because you can never be too sure. But another thing from the theorem of line integrals is that if our line integral was closed, assuming these conditions are met, our integral would just be 0. Because we're subtracting an endpoint from the starting point, and like, let me just do this, for example, it would be the exact same thing. So just like in the FTC, we'll get 0. Which the fundamental theorem of line integrals is just an application of the FTC in multivariable calculus. Anyways, let's rewrite our vector field in a way that will make it easier for us to understand. So that is sine x over 2, sine y of 2. And that is negative 2 cos x of 2. And not sine, cos y of 2. Remember that this vector field is just the same as gradient f. So what this tells us, and I'm actually skipping too far ahead of myself. Let's first check that this is conservative. So let's call this p and let's call this q. Remember that our rule is for a vector field to be conservative, the curl of f has to equal to 0. So let's find the partial derivative of p with respect to y, which here it will just be 2 sine x of 2 cos of y of 2 times 1/2. So change of p over change of y is equal to sine x of 2 cos of y over 2. And then here for q, we have to find the partial derivative of q with respect to x. So this will be, and let me just separate this, negative 2 times negative sine x of 2 cos of y of 2 times 1/2. So this would just be the same thing, x of 2 cos of y of 2. So we can see that, and let me just make sure I'm stating what this is. These are the exact same. All this tells us is that our vector field F is conservative. So now we can go ahead and proceed. Let me make this smaller, move it to the side so that I have some more space. Knowing that our vector field is conservative and that F, our vector field F is just equal to the gradient of multiplied by our potential function F, and that this is just f of x, xy, f of y, xy. We know that f of x, xy is just 2 sine x over 2 sine y over 2, and that f of y, xy is just 2 cos, negative 2 cos of x over 2 cos of y over 2. So with this, just like how we were talking about earlier, we just need to get the antiderivative of those to determine our potential function f. So let's solve for the integral of 2 sine x over 2 sine of y over 2 with respect to x. We can take out the stuff that will be treated as a constant and then multiply that by negative cos of x over 2 times 2. And the reason that is because if we were to call x over 2u and du is 1/2 dx, then in order to have dx be by itself, we'd get 2 times du is equal to 1 dx. So this integral of sine u du would just be negative cos of u, which is x over 2 plus c. So this is where this came here. Oh, sorry, negative 2. I forgot to add the 2 right there. So this is where this 2 came from. Yeah, in total, our antiderivative would be negative 4, actually. Cos of x over 2 sine of y over 2 plus a constant c from our other variable. So this is the antiderivative for the first part. Let me add like a little square right here. There we go. And now let's find the antiderivative for this part right here. So the antiderivative of cos x over 2 cos of y over 2 with respect to y is going to be, we can take this part out since it's going to be treated as a constant, times, this is just sine y over 2 times 2. Same thing here. If u is equal to y over 2, du is equal to 1/2 y, which means that 2 du is equal to 1 dy, and the antiderivative of cos of u du is equal to 2 sine of, and let's remember that u is just y over 2 plus c. So we can bring this all down to be negative 4 cos of x over 2 sine of y over 2 plus a constant c from our other part. And we can see that this is the exact same thing as that. So we can assume that if these two constant numbers are both 0, our potential function f, and let me actually write this down here, our potential function f could be negative 4 cos of x over 2 sine of y over 2. So this is what we will use to plug in our ending points and starting points so that we can compute the integral using the fundamental theorem of line integrals. So now that we solved that, let me just get this all out of the way. Okay, now let's actually solve for the integral. Let's remind ourselves that c f times dr is going to equal to f of x of b y of b minus f of x of a y of a. What this means is we're going to plug in our ending points and then our starting points into this function here, and then subtract the starting point from the end point to get our value that's going to be the answer to our line integral. So our starting point is this point here, P, which at the bottom here says label points are positive or negative 3 pi over 2 or on the x in the x input, and positive or negative 3 pi over 2 on the y input. So we can deduce that this is just, and let me change this into a color red, and let me add this here. This is just 3 pi over 2 and then negative 3 pi over 2 in the x input, and then a positive 3 pi over 2 in the y input. And then at this point here, which is the end point, is a negative 3 pi over 2 on both of the x and y inputs. So this is going to be our ending point, and this is going to be our starting point. So let's plug this into our potential function. Negative 4 cos of negative, and then recognize that this is x divided by 2. So instead of it being negative 3 pi over 2, it's going to be negative 3 pi over 4 sine of negative 3 pi over 4 minus negative 4 cosine of negative 3 pi over 4. And since for our starting point the input was positive, let's make sure we keep that in mind. So sine of 3 pi over 4. Now we could go ahead and solve just like this, but we can also make this easier for us if we recognize that cos of x times sine of x is just equal to 1/2 sine of 2x. So using this identity, we can say that that first part right here with our ending point is the exact same as negative 2 sine of negative 3 pi over 2. Now here for the second part, these are different inputs, but let's remind ourselves that in the unit circle, we're right here, where 3 pi over 4 is here, a positive 3 pi over 4 would just be going this way, whereas a negative 3 pi over 4 would just be going this way. And while these are different points, for cosine, they both give the exact same value of the negative square root of 2 over 2. So for this time and this time only, I'm going to treat this input as if it was 3 pi over 4, since it's going to give me the exact same output, meaning that I can use this identity now, given that I changed that input. So this would be, and let's bring this down here so that it's connected, negative 2 sine of 3 pi over 2. And then using our knowledge of the unit circle again, I'm going to just draw this again since I erased it. For positive 3 pi over 2, it's just going to go like this. And this would give us negative 1. So sine of 3 pi over 2, that's just negative 1. While if we were to go the other way, and let me use a different color for this, it would give us pi, the value of pi over 2, which is just positive 1. So this right here is going to be negative 2 times 1, which is just negative 2. And then we will subtract negative 2 times negative 1, which is just positive 2 from that, which will give us the final answer of negative 4. And this is how you solve this line integral. Once again, once you break it apart, this is a really easy line integral to solve, and there's no sweat in this. This is just something that you can do to cheese your way out of it, but if you were to solve it the long way, you'd get the exact same answer. So yeah, I hope you guys enjoyed and that I was able to help out with this and that I conveyed the information correctly. If you guys have any questions, just let me know in the comments. But yeah, thanks for watching, and I'll see you guys next time. Goodbye.